Okay, imagine this. A star, right? But it's so dense, like unbelievably dense. Single teaspoon. Millions of tons. Now, what happens when something like that, already pushed to its absolute edge, finally tips over? That's the cosmic mystery we're getting into today, this deep dive. It's all about neutron stars and what happens next. Their ultimate fate, collapsing into black holes. And you've shared some amazing stuff with us, scientific notes, detailed astrophysical analyses, even these incredible simulations. So our mission today is to unpack all that, pull out the really key bits, and give you a kind of shortcut to understanding this, well, pretty dramatic transformation. We're going to look at exactly what triggers the collapse, what it actually looks like from different viewpoints, and the signals it sends out across the universe. Okay, let's dig in. So just to set this theme, maybe remind us, what exactly is a neutron star? We hear the term, but what are we picturing?
Yeah, good starting point. It's basically the leftover core of a massive star after it's gone supernova. Think stellar corpse, but incredibly dense. It's packed almost entirely with neutrons squished together like nothing else in the universe.
Okay, neutrons squished together. But gravity's pulling incredibly hard on all that mass, right?
Yeah.
What stops it from just collapsing instantly?
Right. That's the key balancing act. There are these fundamental forces pushing back, primarily something called neutron degeneracy pressure, and also the nuclear forces between the neutrons themselves. You can kind of picture it like internal scaffolding holding the star up against its own gravity.
Scaffolding, like a quantum effect, you mean?
Exactly. It comes from the Pauli exclusion principle, basically. Neutrons resisting being squeezed into the same state. It's powerful stuff.
Powerful, okay. But like any structure, I guess that scaffolding isn't infinitely strong. Is there like a weight limit? A cosmic speed limit for mass?
There absolutely is, and that's where the Tolman-Oppenheimer-Volkoff limit comes in. We usually just call it the TOV limit. It's basically the absolute maximum mass a neutron star can handle before, well, gravity just wins. That scaffolding breaks.
And do we know what that limit is, roughly?
Our best estimates, based on theory and observations, put it somewhere between 2 to 3 times the mass of our sun. Maybe a little more, maybe a little less. Pinning it down precisely is tricky.
2 to 3 solar masses?
Yeah.
Okay, so beyond that, boom, metaphorically speaking.
Pretty much. Beyond the TOV limit, the degeneracy pressure, the nuclear force, they're just overwhelmed. Collapse is inevitable at that point.
Okay, so if a neutron star is already this incredibly dense thing, how does it actually gain that extra mass to get pushed over the edge? Does it just find more matter floating around?
Well, it needs a significant amount. The sources we looked at suggest something like 1 whole solar mass needs to be added if the star is already near its limit.
1 solar mass. Wow. Where does that come from?
Usually one of 2 main ways. One common way is accretion. If the neutron star has a companion star, like in a binary system, it can pull gas off that companion. This matter spirals in, forms a super hot accretion disk, and kind of funnels down onto the neutron star.
Okay, like a cosmic vacuum cleaner. What's the other way?
The other way is even more dramatic. A merger. It could collide and merge with another compact object, maybe another neutron star, or even a white dwarf or a small black hole.
Right, a collision. That sounds messy.
Extremely. But before we even get to the final collapse, that accretion process you mentioned, it's not exactly quiet.
Okay, so things are happening before it collapses.
Definitely. As that matter spirals in and gets pulled onto the neutron star, it gets incredibly hot. We're talking millions, even billions of degrees. And this superheated material blasts out energy, mostly as powerful X-rays and sometimes even gamma rays.
So we could actually see this happening or detect it.
Yes, absolutely. And if the neutron star has strong magnetic fields, the infalling matter gets channeled towards the magnetic poles. As the star spins, and they spin really fast, these hot spots sweep across our line of sight, creating pulsating X-ray signals, like a lighthouse beam.
The cosmic lighthouse powered by infalling matter. That's quite an image.
And it's not always smooth. The accretion can be unstable, leading to flickers, bursts, oscillations in the X-ray brightness, all clues about what's going on.
So even before the main event, there's this whole light show giving astronomers clues. Fascinating.
Exactly. Those signals are crucial. But then, eventually, if enough mass piles on, that critical TOV limit is reached. And then the real fireworks start.
Okay, so the limit's hit. What happens inside this star?
It's incredibly fast. Catastrophic, really. The neutron degeneracy pressure, that scaffolding we talked about, it fails. Instantly. The core just collapses inward under its own immense gravity. The whole star shrinks dramatically, its radius plunging downwards.
Shrinks into what?
Into a black hole. Gravity compresses the matter beyond even the density of neutrons. And as it collapses, an event horizon forms.
The point of no return.
The point of no return. And from the star's perspective, or if you were, hypothetically, very close, this whole process, the collapse, the event horizon forming, takes maybe milliseconds to seconds. It's incredibly rapid.
Milliseconds? Wow. That's almost instantaneous on a cosmic scale.
Yeah.
But hang on. The sources mentioned something weird about how we see it, right? Something about time.
Ah, yes. This is where general relativity really messes with our intuition. It's called gravitational time dilation. Because the gravity near the forming event horizon is so incredibly strong, time itself slows down relative to us watching from far away.
Time slows down.
Yeah. So from our perspective, as the star collapses towards forming that event horizon, its light gets stretched out to longer wavelengths, it becomes redshifted, and the signals appear to slow down, become dimmer, and effectively freeze. It looks like the collapse halts right at the edge.
So we never actually see it cross the finish line. It just sort of fades out, frozen in time.
That's the frozen star phenomenon, exactly. Internally, the collapse is super fast, completed in milliseconds. But externally, due to time dilation and redshifting, it appears to stretch out infinitely and fade away.
Mind blown. That's genuinely hard to wrap your head around.
Yeah.
So the black hole does form, but we just perceive it differently.
Precisely. The event horizon grows and engulfs the collapsing matter, even if we can't see the final plunge. It's a stark reminder that our view of the universe is shaped by gravity itself.
It really is. Just incredible. Does that time effect tell us anything deeper, like about information getting lost or?
Well, it definitely highlights the boundary. Anything that happens inside the event horizon is causally cut off from us. The information about those final moments gets, in a sense, smeared across the horizon from our viewpoint, stretched out forever. It's the ultimate barrier.
Wow. Okay. And you mentioned mergers earlier. Is the collapse different then? More.
Oh, absolutely. The simulations, especially for neutron star mergers, show incredible dynamics. The stars don't just collapse neatly. One star can tidally deform the other, stretching it out. They can be torn apart in just seconds by these immense gravitational forces.
Ripped apart.
Yeah. Huge amounts of neutron star matter can be flung out into space in jets or these long tidal tails. Other stuff gets rapidly pulled onto the forming black hole, often forming a swirling accretion disk around it.
And this is where the heavy elements come in, right? I remember reading that.
Exactly. These violent mergers are thought to be cosmic factories for heavy elements. The ejected material undergoes rapid nuclear reactions, creating things like gold and platinum.
Gold from colliding neutron stars. That's amazing. So the gold in my ring might have come from an event like this.
It's entirely possible. A significant fraction of the universe's heavy elements likely originated in these kinds of extreme events. They also launched powerful short gamma-ray bursts.
And are there other things happening just before the collapse besides the accretion signals?
Yeah, there can be. Sometimes, just before the final collapse, the immense stress on the neutron star's crust can cause it to crack and shift. These are called starquakes.
Starquakes, like earthquakes, but on a star.
Kind of, yeah. They can release huge bursts of energy, powerful shocks, and some simulations even suggest you might briefly get something like a black hole pulsar, where the collapsing star's magnetic field interacts violently with the forming black hole, shooting out magnetic winds and flares.
So much drama packed into such a short time. Okay, with all this happening, the accretion, the collapse, the mergers, the quakes, how do we actually know this is going on light years away? What are the signals we look for?
We have a whole toolkit now, which is really exciting. The big one, relatively new, is gravitational waves. Detectors like LIGO and Virgo can hear the ripples in space-time from spiraling neutron stars in the moment of collapse or merger.
The universe literally shaking.
Literally. Then there are the electromagnetic signals we talked about, the X-ray and gamma-ray bursts from accretion, and those powerful jets formed during mergers.
Right, the light show.
And after the main event, especially after mergers, we often see an electromagnetic afterglow. This is the fading light across different wavelengths, like visible light, radio waves, X-rays, as all that ejected material cools down over seconds, days, even weeks.
So it's like putting together clues from different messengers, gravity and light, to build the picture.
Exactly.
Yeah.
Multi-messenger astronomy, we call it. Combining gravitational waves and electromagnetic signals gives us a much richer understanding of these incredibly energetic events and the physics of matter pushed to its absolute limits.
What an incredible journey. We started with this dense ball of neutrons held up by quantum pressure.
That fundamental balancing act.
Then hit that critical TOV limit, the point of no return, and watched it undergo this incredibly fast internal collapse.
Milliseconds.
But from our perspective, it becomes this bizarre frozen star due to time dilation.
Yeah, that relativistic weirdness.
Then all the fireworks, mergers, jets, starquakes, and even creating cosmic gold and platinum.
It really covers some of the most extreme physics in the universe.
And this isn't just theory, right? You mentioned the sources. This is backed by real data.
Absolutely. It's grounded in incredibly sophisticated computer simulations run at places like NASA and Caltech, but crucially, it's confirmed and refined by actual observations, gravitational wave detections, telescopes picking up those X-rays, gamma rays, and afterglows. They all feed into and support this picture. We're really starting to see these events happen.
Amazing. So next time you hear about some distant cosmic flash or ripple in space-time,
Yeah.
it might just be the universe forging a new black hole, violently reshaping space-time, and maybe, just maybe, cooking up the elements that eventually find their way into everything around us, even our jewelry.
Makes you wonder, doesn't it? What other extreme cosmic events are out there, quietly shaping the universe and the very stuff we're made of in ways we haven't even figured out yet?